Because I'm curious, as I was mentioning, in very cold planets, if the temperature outside is minus 30 degrees Celsius, you breathe that air in, and what is the typical tissue temperature? Maybe around 40 degrees Celsius. So that's a big enough jump. So I'm just curious if that is fine. So how much is 30 Kelvin converted to Celsius? Huh? Minus 240. So the delta is 240 Celsius approximately. So hence it is not possible. Uh, and I think if
the delta to 30 Celsius, each unit Kelvin is almost each unit equal to Celsius. So del T will be 30 degrees Celsius. Like if you take absolute temperature 30 Kelvin, that is what it wants to be. But if you look at the difference of the let's say 30 Kelvin difference, we can straight say it is 30 degrees Celsius difference also. Because each unit is like equal to each other. Fahrenheit we have to like the 1.8
yeah, so I need to explore more on this. Whether I mean it is fine at regular temps, but if it is indeed that cold, that 30 degrees Celsius difference, I wonder like when I go outside and do things, when I am really outside in that temperature, whether the tissues like we are talking about the very outer tissues, right, inside the nose, whether they still stay at 40 degrees Celsius or not. Because I once heard this funny story, and it's a real story that in the colder regions of Canada, which is similar to what we have in Brookings, like if you go outside, and in fact even in Brookings, like if I have a cold, the mucus coming out would freeze when I'm outside. And for that matter, if you take a shower and just go outside, your hair would freeze, because the water would freeze. So that is interesting. I did not think much about this temperature difference, but what happens in the extreme climate zones. But anyways, let's assume that it is incompressible and we can use the version of Navier that we have found and see what we can deduce based on, for example, what the Reynolds number could be in a certain region of the airway. Okay, so as a brief recap, in addition to this, what we did in the first 2 days primarily was we tried to model particle transport. We started out with equations that are very idealized in any random geometry, and then we tried to see if we induce some kind of curvature which is inspired from the anatomical geometry. We induce certain sizes of the cross sections, what we can deduce in terms of the particle transport trends. And then towards the end of yesterday, we realized that yes, particle transport in terms of how the fluid field, the flow field talks with the particle transport is through the drag force, right? So if you look back at our calculations, you'll see that we assumed a realistic flow rate. So the drag force effect was more or less similar, even if it is a very complex geometry, whatever the drag force would have been in that flow field. But now that we are trying to think about the fluid dynamics in the respiratory tract, things are a little bit trickier. Because as we saw, like if you have a very complex topology of the domain, which we do have, topologically it is similar to a pipe. But a pipe flow won't have those different vortex dynamic features, for example. It will be straight streamlines or smooth streamlines. On the other hand, we do know that we come across this very strong vortex, coherent vortex patches in the inner flow field. So the challenge is slightly different here. The first thing that we are going to do today is non-dimensionalize the Navier-Stokes situation and see what we can tell by simply looking at which terms in the Navier-Stokes equation would be dominant. And as a result, that would eventually guide us what we would need to do in the full-scale numerical simulations, because analytical models can only go as far in terms of replicating the inner flow. While modeling the the flow field through numerics, we have to make certain decisions like whether it's an unsteady flow field, or whether it's turbulent, or whether it's laminar. And those deductions could be obtained by what we are doing now, by looking at the various flows and looking at which terms are dominant. Before we start the simulations, the computational simulations tomorrow, I would still want to show you one case where I try to generate the flow field in an idealized domain, and the differences that we will see in terms of a full-scale model generated flow field versus the idealized flow field would tell us why this is probably not the best idea to idealize the geometry while trying to understand the flow field as such. The particle transport is fine, and as I showed yesterday, that last problem that we did with the MATLAB code on what is the density needed for a certain particle of a certain size to deposit, that is quite interesting, and it will be worth following up on that. Okay, so today let's begin with. So this is day 3. So non-dimensional analysis of the fluid dynamics equations. So we are going to assume incompressible flow. So let's write down the Navier-Stokes for that. So for incompressible flow, which is in this case the inhaled air flow, conservation of linear momentum leads to the Navier-Stokes equations. So rho material derivative of the velocity field minus square root of p plus mu Laplacian of v. So let's break up the material derivative, and I'm taking rho to the other side. So we have del v del t is v dot grad v minus 1 over rho grad of p plus mu over rho Laplacian v. So this is the dimensional equation. Let's now try to non-dimensionalize it. So we are going to pick a velocity scale here. Yes.
What am I taking this body force now?
Huh?
Body force.
We are not taking the body force. The body force would be, as we know, an added term over here. But we are not taking the body force here. The understanding that we are trying to get at, as I just was trying to let to you guys, to figure out what are the dominant terms. So for example, if we see that the del v del t term, whatever that term is after we non-dimensionalize, if that is a dominant term, that means that while simulating the flow rate, we have to think about the unsteady nature of the flow. On the other hand, if we see that that term is negligible, viscosity is dominant, we can possibly think about a laminar solution. So either way, whether you consider the body force or not, it doesn't make a difference. If you're trying to analyze the dominant terms in the equation, you can do that with the body force. Okay. Now for the velocity scale, let's use a slightly different terminology, u instead of u naught, that I was taking, because I want to make a clear distinction between what we have been doing for the first two days, which was geared towards understanding the particle transport compared to now when we're trying to understand the flow field. So let the velocity scale be u. So as a result, the non-dimensionalized velocity field v is v over u. Again, note that this v is different to the v that we had in the first two tests, where the v was standing in for the particle velocity. Here we are talking about the velocity in the flow field. There is no particle as such. Let the time scale be t. So as a result, the non-dimensionalized time scale is t over caps t. So we have taken care of the v. We have taken care of the time. So this t. What else is left if we want to non-dimensionalize this equation? The pressure. So there are actually two choices of pressure scales based on whether the flow has a high Reynolds number or a low Reynolds number. So the two choices of pressure scales, let's call that this P. So this P is mu u over L, where L is a characteristic dimension when we have a viscous domain primarily. So this is a viscous scale, and the Reynolds number is small. The other option for P is rho u squared when we have an inertial scale for large Reynolds number. So let's apply both into the dimensional equation and see what we get. So therefore, with the first one for low Reynolds number, P is mu u over L. This leads to Stokes number times del V prime del T plus Reynolds number V bar prime dot grad V is equal to minus grad of P plus del square V bar prime. Uh, Say again? Yeah, here. Rho u square by L. Some people take half rho u square. Yeah. Numerical factor doesn't make any difference. Okay, so let's look at this equation first. So the Reynolds number being low, this is the convective part. So that is going to be negligible. And that is pretty much that we can enforce on this equation. So this part can be neglected because the Reynolds number is low. Now this is until now, and even if we do apply the inertial scale, which I'm going to do next, we are still not really connecting this to what is happening in the respiratory pathway. That is going to happen next. But as of now, if you have small Reynolds number, you can ignore the convective part. And just to think a little bit ahead on where you might come across small Reynolds number in the respiratory pathway, can you guys guess that Reynolds number is going to be small in our respiratory tree? No. The cross-sectional area is larger, but the flow is also quite fast. It is actually in the very final channels of the lungs. So as the air goes deeper, once it goes to the higher generations of the bronchial pumping, that's where we encounter the low Reynolds numbers. And those have been studied experimentally. I'm going to come to that one next, later on. But just to know that we have ignored the contractive part, but we still don't know about the other terms in connection to the respiratory flow rate, and there will be other assumptions that we can further place on this equation. Okay. Yes.
For the time we had used the convective scaling, non-dimensional, it reduces the relaxation.
Say again.
Non-dimensional is the time.
Yes.
The scaling we had used is for the same as the time. Shouldn't it be a viscous time?
I have not said much about the time scale, have I? So it is just a characteristic time t. You can think of it as the relaxation time is inherent to the particle dynamics. We are not thinking about particle dynamics anymore.
Yes, but then the slope will come once we have the relaxation.
The Stokes number will come anyways, whatever characteristic time you might take. The Stokes number, what I showed is if you think of the characteristic time as the particle relaxation time, a part of it is the Stokes number. Right? So Stokes number times, but that does not.
T dash just for the sake of
Which one?
the Stokes number equation, T dash.
Oh yeah, right. That I missed. So this del t prime should be the. I have a bad habit of missing this line.
So generally you can just avoid all the dash for the next to avoid any confusion.
I don't know if you guys noticed, I also corrected my notes because I missed this prime sign over here. Okay, so this is for the low Reynolds number. Let's look at the large Reynolds number. So now this P scale is rho u square. So we have 1 over Struhel number del V prime del T prime plus V prime dot grad V minus grad of P plus 1 over Reynolds number plus n of P prime. So now over here, of course, the viscosity term, this RE being large, we can ignore that safely. But we will further develop this equation for the respiratory pathway to see what else we can tell about it when the Reynolds number is large, which is what happens when the flow is within the upper respiratory tract for sure to the larynx. It goes through a transitional regime through the trachea and in the conducting region of the lungs, which is still around generation 3 or 4, but still safely when I'm modeling the airflow till generation 3 or 4, I assume that it is a large Reynolds number regime. As I said yesterday, it is difficult to segregate from high Reynolds number to transitional regime in the same simulation. So this over here at least can be neglected from general flow consideration. Yeah, just for clarification, because I myself always confuse between Stokes number symbol and Struhel number, so this is the Struhel number. Okay, so let me write down some comments now in connection to the respiratory flow field on what the typical trends of the flow would be like in different regions. So it is seen that RE, the Reynolds number is quite high. Again, for clarification, I think in the first 2 days when I wrote RE, I probably could have used REP for the particle Reynolds number. This is the Reynolds number of the flow field. So let's not confuse between the day 1, day 2 Reynolds number with the Reynolds number we are talking about now. So it is seen that the Reynolds number is quite high in the upper respiratory tract till at least the larynx and is very low when we enter the deep lungs. Again, in the community, especially when mechanicians like us are trying to model the fluid mechanics in the lungs, different people define what is deep lungs. So when I'm saying deep lungs, I'm talking about the regions that are after the conducting zone of the lungs. So from generation 5, 6 onwards till generation 23. Okay, so when the flow is at high Reynolds number, which is in the upper respiratory tract, the internal flow become turbulent at the high Reynolds number. And as we go into the deep lungs, we can safely assume that the flow is going to be laminar, and we can control our simulations accordingly. And a laminar at low RE at the further recesses of the lungs. So since we are going to start the simulations hopefully yesterday for the upper and the central airway till the low bronchial generations, we are going to use turbulence modeling schemes. We are going to use large eddy simulation in our work. We are not going to simulate anything for the deep lungs, at least in this course. But if you do, at least the benefit would be you don't have to worry about using turbulence schemes. You can use a laminar viscous model. Okay. Okay, let's now look at further evolving this second equation and see what else we can derive from here. And the reason why I decided to use this particular equation is because I came across some experimental data where they looked at the ratio between the Reynolds number and the Suhol number, so RD over ST. And if we can bring the RE on the left hand side, of course that is trivial, but we can correlate that form of the equation with what we see from the experiments to enforce some more conditions on this equation.
So let's typical physical magnitudes of the velocity in the bigger pathways of the lungs.
So yesterday in the problem I assumed 5 meters per second. That's a good question. Let's do a quick calculation. So for example, if you think about this particular geometry, what do you think the cross section would be area as a nostril? Maybe 2 centimeters, 30 centimeters. So if I pitch the area to be 4 centimeters square, and the flux, as I said, for relaxed breathing or even for moderate breathing, the Q is 15 to 30 liters per minute. So let's pick the mean to be 20 liters per minute. Therefore, the V is going to be Q over A. give me 20, convert 20 liters per minute to meters per second. How much is that?
So liter is like 1000 cc.
This lesson is for the kind of use the internet. 0.83 meters per second. 4 centimeters square to 4 meters square. To 2 meters square, how much is that? Huh?
This is velocity.
This is the velocity. Okay, okay. So 0.83 meters per second.
This is liters per minute.
Are you sure about the
calculate 20 into 1000, that will be 20,000 cc per minute. Then you divide by 60 into 4.
20 liters is 1 liter is equal to 1000
cc.
Okay, let's give me the correct number or the confirm number. Huh? 0.083? 0.83. Okay, he already gave me that number. Someone else confirm if it is indeed that? 0.8. Okay. So, where do we stand in terms of that? So, this is just the flow rate going in, the velocity going in through the nostril. Where was your question coming from?
What is the velocity, like magnitude in our upper pathways?
So, let's assume that this is on the order of 1 meters per second. What we had assumed was 5 meters per second. Now, I have to check the cross sections as we go further in as things get narrower, and that can probably, if it gets wider, that would make it more than this or bigger than this. But the order is still going to be the same. So let's assume that it is on the order of 10 to the power 0. But the good thing is while trying to simulate this flow conditions, we gathered, and this is a few years back, around 5-6 years back. So we had this breathing apparatus that the person is supposed to breathe in and breathe out, and we collected the flow rate speeds in real subjects. And there is an empirical formulation that we had derived as well, which I'm going to show before we run the simulations. So whatever flow rate we would decide to simulate eventually. So even to complete the problem that I proposed yesterday, we just tested 2 particle diameters. We can apply the realistic breathing rates. I'm getting more curious. Let's quickly take a look at the problem that we solved yesterday. So over here, the A was the tau Vf square over L0. So this, if we change it to, so if you think about this to be 1 meters per second instead of 5, so this becomes around what, 3.2 no, rho Vf squared. So let's do this calculation later on. So what happens if you rather take it as 1 meters per second? In fact, let's do it now. Why don't we do it now? We have time. So let's go to this. So we had A as tau Vf square over L naught. So let's just pick the 100 micron case. You can go back to your lecture notes yesterday. Let's pick the 100 microns case. We saw that tau was 0.031. So let's use that. So this would be 0.031 times, we are now picking it as 1 meters per second as the velocity, divided by L naught. And L naught was 0.05, right? How much is this? 0.62. Okay. Anything else that is changing in the main equation? We have the equation was tau Vf square over L naught times t plus tau e to the power of minus t over tau minus 1 minus L is the equation that we were trying to solve numerically. So tau Vf square is now 0.62. The relaxation time stays same. It is not dependent on the flow field, right? So let's revise the value now in the code. So this becomes 0.62. V was the relaxation time, that's just same. So let's run this. So what did we have before? We had before, let's go back. So before, the solution for the time interval was 0.0046. Now we have 0.62, 0.0254. So it did change as we expect that it would change. But still, it is small enough that it's clear that it's going to be positive buffer away. So that tells us that once we become more precise, this was just an estimate, right? When I plugged in those numbers for the velocities and whatnot. But once we plug in the real numbers, this could be a valid project that anyone here can solve. Okay? Any questions? Okay, let's go back to the document viewer. Okay, so as I said, we are trying to utilize the experimental data. We are going to modify this equation a little bit, basically get Reynolds number to the other side. So let's reformat the second non-dimensional equation. So therefore, Reynolds number over Strouhal number del V prime del T prime plus Reynolds number is equal to minus Reynolds number grad P plus Laplacian of V prime. If you guys are looking at the lecture notes, I see that I made a mistake of skipping the prime on the time. So if you see that and it is obvious that it's my handwritten typo, just correct it on your own. So now let's look at what we have from the experimental data. And since I'm drawing it by hand, it is going to be a rough sketch, but you'll still get the generic order of magnitude. So I'm going to start, so on the y-axis we'll have Reynolds over true hull. It will start from point 0001, then point 01, then point 1, then 10. And on the x-axis, we will have the bronchial generations. But we will start from where the larynx is. So we move from the upper respiratory tract deep into the lungs. So the values, they start from around 10. Let's note down this as well. So 2, 3, 4, dot, 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 till 20, 22, 23. So they go like this. So this is the generic trend of the RE over ST. So as a result, now what we can tell about this main equation. So when we are still in the laryngeal region in the upper respiratory tract, this term is big enough. That means the unsteady component is still significant enough. But as we go further in, the RE over ST dies down, which tells us that the unsteady term could be ignored while simulating the flow field. But what else is happening? We know that in the upper respiratory tract, Reynolds number is large. So these terms would still be there. The convective term would be there. The pressure term would be there as well, of course. But as we go further in, we also know that the Reynolds number dies down. So then this convective term goes to close to 0. This term would also go close to 0. And we will be left with just the viscous term, essentially, in the equation. So let me write these comments down. So in the upper airway, the Reynolds number is large, and so is the RE over ST. So as a result, both both the unsteady and the convective components are dominant. Okay. So let me just, for the sake of clarification, this is experimental data. The unsteady term, the convective, and the viscous. So while modeling the airflow, we have to assume that it is unsteady, the flow field, and simulate it accordingly. When I first started out in this track of research as a postdoc, because I was working in a group where probably I was the only fluid mechanician, so there was this understanding that it is okay to model the flow as laminar even if someone is breathing at say 15 liters per minute, which is what in the clinical world they assume it's relaxed, steady breathing when someone is sitting down. And I did model them as laminar flow. And some of those works also have been published. So probably that was not the most Puritan way to simulate if you think about the fluid mechanics of the system. And the second error that I did, and these things we learn over the course of years, right? Eventually I realized that things are turbulent, so I started modeling them as Ram's models. And then I realized that the vortex features are very important in this flow field. And those happen over very short time scales. And what Rams does is averaging, right? So it does get something, but that is probably not what is physiologically realistic. So then we had to. By then I was done with postdoc and I had my group at SDSU and we tried to gradually move into biology simulation. So nowadays, all the papers that you will see coming out of my group, they use typically, as long as we are in the upper respiratory tract, the LES simulations. Okay, so this is for the upper respiratory tract, which is what we are going to simulate in this course. In the deep lung, the Reynolds number is small. Therefore, along with the fact that from the experimental data we see that the first term goes out, the second term would fizzle out as well because the Reynolds number is small, so there is no convective component. So therefore, the convective component is small, along with ignoring the unsteady term, because RD over ST is small. So RD over ST, if you take half of it, what is that? It has a name, and I'm sure you guys use it more often. Many of you might use it more often than even I do. Isn't it the Omersley number? That's what I figured out. It's the Omersley number. So it's the Omersley number. So this gives a measure of the importance of the unsteady term in comparison to the viscous term. So as and when you guys write papers for this kind of systems, I think, especially if you are going to venues where fluid mechanics is what people are worried about, you need to justify what you pick for your simulation parameters, and this is one way to do it. Unfortunately, I did not note down the citation for this experimental data. If you are interested in the future, just let me know. I'll take it out.
So,
Yes.
so for the low RD region, like we should look at the first moment instead of taking
I decided to use this because I had the experimental data. Now, if you do take a look at you are right. So if you do take a look at this first equation, what happens then? So you can ignore the convective term. What else are we doing here? So the Stokes number, we know that as we go further in, the Stokes number is related to the Reynolds number. So that unsteady term would go down as well. So eventually we will reach the same conclusion, even if you use the first equation. I decided to use the second equation for both the regimes just because we have this support of the real physiological data to compare against. Okay. Let's do this as well before we stop. Okay, so you guys have the printout for this. So this is coming from a work from my group that has not been published yet. but it's on archive and it is going through peer review right now. Uh, since the projector is not very thin, why don't you open it up? So here what we did was, it is exactly this by the way, finally what we are saying here is the exact same model as this one. So we simulated inhalation through this geometry, and this is a 30 liters per minute simulation using LES model. The thing that I want to point out is the secondary flow features that are popping up in this domain. So the secondary flow patterns, and this is 30 liters per minute inhaled airflow. Now, going by this little calculation that we just did, if we had picked 30 liters per minute, this number would have been a little higher, right? So probably a little over one. Now, if you think about what is going on here, it is 30 liters per minute. The flow is not only entering through the nostrils, it is also entering through the mouth. So the flow is getting broken up. But still, if you look at the range, it is fairly thin in that zone. And then we are in that kind of a thing, the values that you guys calculated. But as we go further downwind, things are getting trickier because now all the flow is getting merged into these very small cross sections. To get an idea about how small the cross sections could be with this frame, so which is so it is somewhere over here, basically. So this is how tiny it is, and it is taking to 30 liters per minute flow. And as you can see, the cross section lies even within this kind of penetrative depth. So the first one is the velocity field, the second one is the pressure field, the third one is the vorticity magnitude. Now the interesting thing is, since we are talking about the secondary flow patterns, is to forget the first two for now, focus on the third one. We see that there are some vortex regions in the upper respiratory tract. Like if you change the range of the
Here you have only taken the positive, just the magnitude.
just the magnitude. So it's the magnitude
More.
the resultant of resultant of omega x omega y. That's it.
But if we take like the absolute means instead of absolute magnitude, if we take both positive and negative, isn't it better like you can show the different patterns like something in negative positions will show that the flow is going in the other direction.
Yeah, we have been thinking about that whether we should do that. The thing is, the reason why I took it is because at the end we were trying to study how the vortex regions are impacting the particle transfer, right? And as it's not here yet, but as I will show, we were trying to develop a truly idealized reduced order model where we can use this vortex magnitude as the strength of the bottom vortex. Right? So when you collapse everything to a 2D plane, if you use omega x, omega y, omega z, you can still do that. But the thing is, if you think about the direction of rotation for each of those vortices, we have so over here, if you see the axis, y is up, c, and then x is going into the screen. So omega y would be like this, right? And omega z is like this. So let's first focus on omega y. It is giving sort of like a swirling motion. The particle is going in. Now whether that omega y can do much to the particle, it would do, it can do some effects, induce some effects on the particle, but can we capture that effect on a 2D model? We cannot, because we are restraining the motion of the particle on that 2D cross section. So we could not really just use omega y, because then it will be misrepresentative. Similarly, for omega z, it can move the particle around like this, but then again we are doing a 2D model, and if we just pick omega z, then also it will be misrepresentative. Omega x is fine because the 2D model is like this. So basically I'm looking at a rectangular domain which is equivalent to this. The omega x is going to move it towards these walls, but then if we don't include the effect of the omega y and omega z, then also that effect is misrepresentative. So the best possible solution that we thought in terms of replicating the vortex induced effect on the particles would be to take the effect of all the three components.
You're taking a root mean square of omega x square over 2
You can directly output the velocity magnitude.
Oh,
yeah. But to your point, if you are rather, instead of the plane being on this plane, if you are looking at a plane that is cross-string, then perhaps you can think about other magnitudes, but then again you have to restrain the particles on that plane, which is tricky. Does it make sense what we are trying to discuss? So that's why I picked the vorticity magnitude, but this is a very new line of research in the sense no one has looked at reduced order models of this kind of systems. They have been simulating this kind of airflow for the last 10 years, and you'll see plenty of work where they're just using the commercial simulation packages and deducing different things. But understanding the flow field, what is going on, is still not there that prominently. And without that being there, whatever you have is just a set of numerical experiments, right? So this, and this is something that we will ask all the time. So this works for this particular subject. What about someone else? So the holy grail over here is to figure out some kind of generic trend. And to extract that generic trend, you need to think about a little bit on what you can derive analytically. And that's why we are trying to go towards a reduced order model, which I'm going to discuss a little bit in this course later on. But for now, let's focus on the secondary flow patterns. So since we were focusing on the vortex formations, over here, yes.
Could you please comment on this pressure computation? This pressure is like minus 50 pascals. Is it like base pressure on the air?
This is absolutely right. Don't worry about the atmospheric pressure as such. We induce zero. So basically,
gauge pressure, right?
gauge pressure. So the 0 pascals was at the opening, the inlet openings, and that's why it starts from red over there, and the negative pressure drives the flow. So basically, gauge pressure, delta P, whatever you call it. Okay, so we are focusing on the vorticity magnitude. So here I just a zoom in visual of the third diagram over there. And to your point, that F, G, and H are the X, Y, and Z components. So to your point, the panels F, G, and H, they are the omega X, omega Y, and omega Z. So as you can see, the omega X is small, omega Y is slightly bigger than omega X, but still small. The main driving thing is omega Z. But if we just use omega Z, then we miss the point of the reduced order model. So we have to include all the effects together. And then what we are doing in our work is break up this domain into tiny chunks of vortex patches and put a point vortex in each of those chunks. And I think if you look at the printout, it is clear because you see those black dots. Those are the locations of the point vortices, and we are trying to develop the reduced order model accordingly. That is a different discussion. What I'm trying to focus on is, or basically highlight is, the secondary flow features can have a distinct impact on the eventual particle transport that we are doing today. So let me write down some comments over here. So just to clarify, this is X vorticity, this is Y vorticity, and this is Z vorticity. I have already included the coordinate directions over here. So x is into the plane, and this is the vorticity magnitude. So in the upper airway, owing to the large Reynolds number, the convective term is dominant. And we have already discussed about certain points that I have over here. Let's quickly jump into what is the source of this vortex formations. So this is happening as a result of both the shearing action and the centrifugal force of the flow. So there is an imbalance, and that imbalance creates this strong vortex patches. Let me write down this statement first. So as the fluid particle moves around the around a bend, as I said, even in the nasal space, there could be some vortex formations because there are also some topological deformations where the fluid particle might have to navigate a bend. But it becomes more prominent when the airway is most constricted, which is near the larynx. So, as the fluid particle moves around a bend of fluctuating curvature, the imbalance between the centrifugal force and the pressure gradient leads to instability, and leads to instability and the resulting vortex formation. Okay, and yes, okay. Any questions until now on this?
So the gravity influence also.
The gravity influence is there, yes. As I think I have, no, this is in my research talk. So the gravity influence could be there. Yes.
What I say in the diagram of the gravity is.
Yeah, so these simulations we do include the gravity. Is there, right? Yes, yes, we do include the gravity. But the thing is, the gravity effect is more prominent on the particles rather than on the flow. So if you simulate with gravity, without gravity in your flow, you will not see much difference. The particle transport, you will see some difference. Okay, let's close it here.
So we can start at maybe 35, which is from now. You can have the inside output is there and let's start. So just as I understood also.